This video is going to talk about commutators and the commutator group. So first let's start with commutators. For any elements A, B in a group G, their commutator is denoted as A dot B or comma B if you wish. And it's given by this thing. It's A inverse B inverse A B. So clearly if A and B commute, then this commutator is just the identity. Otherwise it has some nice properties, but it's not identity. Alright, so the first nice property that we want to show is that if both of them, so G acts on some set S, right? And let's say that S is something like 1 all the way till n, and so it might be like A is some permutation on these elements in S, right? So it's like 1 2 3 4 5 something, I don't know, it's like involving a lot of stuff, and then there's M somewhere, so it's involving the first M numbers or something, or maybe like some other numbers, and then who knows. So all these numbers that are involved in A, these are called the support of A. So I write it as sub of A, so that's just all the elements in S, so all S in S, such that A of S is not equal to S itself, as in they are moved essentially, right? Okay, yeah, that's awesome. So now if support of A and support of B, both of them only have one element in common, right? So if they have no element in common, then we can like just switch them around, like not caring all that much, and in that case they just commute, and the commutator is just the identity. If they have one element in common, right, so let's call that element as X. In that case, this commutator will actually be a 3 cycle, and we are going to see how that happens. So first let's try to put X into this thing. So it's A inverse B inverse AB of X. Okay, so first thing that happens is you get B of X, and B of X cannot, so we know that X is in the support of B, right? So B of X cannot be equal to X. Now B of X should not be in the support of A, because we know that B of X is in the support of is in the support of B, right? Because in the end B has some order, right? So you just like keep applying B a lot of times, maybe like B power n, let's say the order of, or who knows, okay, B to the power of order of B, right? That is going to be identity. So you can think of it as B power order of B minus 1 times B of X. That is supposed to be equal to X, right? Yeah, so clearly B of X must change, right, when you apply B on it, because if it doesn't change, then this equation does not make sense, right? Because in that case it would just be B of X over here. So clearly B of X is in the support of B, but it cannot in that case be in the support of A, because if it is, then our assumption of X being the only thing in the intersection of the supports, that would be wrong. So in that case, when we apply A on this element B of X, it doesn't really do anything, and so all we get is just B of X like that, and then we'll be inverse of that. So yeah, we just get X itself, and then you apply A inverse on that, right? So A inverse of X, and so what we have just figured out is that X is going to get moved to A inverse of X. Alright, cool. What's A inverse of X going to get moved to? So instead of applying this commutator on B of X, we are going to now apply it on A inverse of X, right? So once again the same thing as before. A inverse of X cannot be in the support of B, because, well, yeah, I mean, if it's in the support of B, then there are two elements which are in the intersection of support. So clearly A inverse of X is in the support of X, right? Because apply A on that element and you get X, and these are not equal, right? Obviously these are not equal. So yeah, okay, cool. Right, So what this means is you can apply b on it and it won't change it in any case. So then this just becomes a inverse b inverse a inverse of x. Or I should just say a inverse of x. Yeah, that's better. And this cancels in that case, and so you just get a inverse b inverse of x. Now once again, b inverse of x is not in the support of a and does not in the support of a inverse, because it's just considering like the same elements once again. And so this just becomes b inverse of x, right? So a inverse of x gets mapped to b inverse of x by the commutator. What about b inverse of x itself? Well, it's going to be pretty much the same as this one, like what happened to a inverse. First note that b inverse is just, well, x, so it just becomes a inverse b inverse a of x. But then a of x is not in the support of b and does not in the support of b inverse, so this is like not going to matter. But then a inverse a, that's just x, and so we close this cycle like that, right? So that's the 3 cycle that we're talking about. Now what about the other elements? What happens to them? So if you consider any other element y which is not in any of these, then okay, so y is either possibly in the support of b or not in the support of b. Okay, so suppose it is in the support of b. In that case, b of y is what we're going to deal with. Well, b of y should not be in the support of a, right? And obviously y if it's in the support of b, it must not be in the support of a, right? So apart from x, there cannot be any other element which are in both which are in the support of both a and b. But yeah, so either b of y is in the support, so either y is in support of b or it's not. Well, if it's not, then like you just have y over there. If it is, you have b of y. Now clearly b of y, it cannot be in the support of a, because if it is in the support of a, well, b of y itself is obviously in the support of b, so it's in the support of both a and b, and that's violating something, right? Unless b of y is a inverse of x, right? Yeah, so if b of y is not a inverse of x, unless b of y is not x, right? So if b of y is not x, which only happens if y is b inverse of x, right? But we already covered that case, so we kind of know that this inequality holds, and so in that case we know that it is not in the support of a, right? Yep. Yeah, because it is in the support of b, obviously. So from there we can say that okay, this a does not do anything to it, and so you just have the b inverse applied on it. So then b inverse b is just y, and then you have an a inverse applied on it. But remember, y is in the support of b, so it cannot be in the support of a, and so this just becomes y itself. So nothing much really happens to y, right? If it's in the support of b, that is. Well, if it is not in the support of b, then you just get y and then a of y. So yeah, a of y, it could be just y if it's not in the support of a, and then like after that we kind of know what's going to happen. It's just gonna be y itself. But we want the more interesting case where it is in the support of a. If that is the case, then it's not in the support of b. The only way it could be is if a of y was actually equal to x, which is to say y was a inverse of x. But we already covered that case, so we can say that okay, it's not in the support of b, right? Yeah, and thus not in the support of b inverse as well. And so then this b inverse doesn't really do anything to it, and it's just get a of y, and then a inverse of that, well, that cancels this, you just get y. So in both cases, that is both the interesting cases where y is in the support of a, or if it's support of b, you just get y out of it. And if it's in neither support, in that case, well, this whole thing doesn't do anything to it, right? Every single permutation in this commutator doesn't do anything to the element y, and so it just remains the way it is. And so what we have proved is that this commutator is exactly just this 3 cycle, right? And so this is really useful sometimes, because like you can create moves to games like Rubik's Cube with this thing, which I'm not going to go over, but it is useful. Okay, so that's about commutators themselves. You've now got an idea of how to use it. Let's go to something called the commutator group. So the commutator group emerges from a very simple sort of question, that if you have a group G and a normal group N, when is G by N abelian, right? That's the simple question. So if G by N is abelian, then you have some nice stuff happening. Firstly, you have this homomorphism, the natural homomorphism by normal subgroup thing, which sends stuff from G to G by N, right? And its kernel is just N, right? Yeah. Now, if it just so happens that G by N is abelian, then what's going to happen is that for any two cosets in G by N, right? So let's say C1 and C2, their multiplication is just the same. Doesn't matter what order you have, right? Yeah. Now C1, C2 are obviously like something like phi of some x and phi of y, where x, y are elements of G. And so you are saying that for any elements x, y in G, what's going to happen is phi of x, phi of y is equal to phi of y, phi of x. But then since phi is an homomorphism, essentially what we're writing is that phi of phi of x inverse, so you multiply by phi of x inverse on both sides, right? And then phi of y inverse, right? So you first multiply by phi of y inverse from the left on both sides, and then phi of x inverse, right? And then phi of x, phi of y, psi of y. It's not phi, sorry, it's psi, right? That's equal to the identity in G by N, which I'm just going to write E for now. But what this is telling me is that psi of, well, you can use the property of homomorphism, and just becomes x inverse y inverse xy. That's equal to E. But that means that x inverse y inverse xy, so I don't actually write E over here, because we know what the identity element is. It's just N. Yeah, the coset N, that is. And so x inverse y inverse xy, this is supposed to be in the kernel of psi, because of the way that kernel is defined, right? Yeah, right. So what we just showed is that for all xy in G, their commutator x comma y, that is going to belong to the kernel of psi, which is just N. So for G by N to be abelian, this is going to happen. And so we can construct this new sort of group, which is called the commutator group. So people write it like as G comma G. I do not like this notation, but I'm still going to stick with it. So it's basically the group generated by all the commutators. So yeah, it's a group generated by all the commutators x, y for x and y in G, right? Yeah. Yes. So notice that these commutators themselves are all in the kernel. So like any sort of thing generated by these commutators is also going to be in the kernel by the closure property. And so this group is actually just in the kernel N, right? Yeah. And so what you will also notice is that this is actually a normal subgroup. And so if so any normal subgroup that has the quotient G by N being abelian, that contains this other normal subgroup called the commutator group of G. Yeah. I should kind of show that this really is a normal subgroup, I think. Yeah, I think so. So Okay, so it's generated by the commutators essentially, and what we are looking for is g, g and then some element in this, like, let's not say small x, let's say, I don't know, what to call this thing. It's called h, and then g inverse, where h is in this commutator subgroup and g is any group in G. So we want to show that this thing is actually in the commutator subgroup as well, right? Okay, cool. So what we want to do is be able to write this as a commutator of something else. Yeah, that's straightforward, isn't it? Okay. So how are we going to do that? Is GG inverse over there. We could have the identity or something. Never mind all that. So it's made up of all of those. Yes. So my memory is a little rusty on this thing, but so this should actually just belong to that, so that it's a normal subgroup. Yeah. Okay, let's think about it. So H is basically made up of commutators, right? So an inverse of a commutator is also just a commutator in the end. So what happens, it looks something like this. It's G, then you have x1 inverse, y1 inverse, xy, and then that times some other commutator, and so on, right? So this times maybe like x2 inverse, y2 inverse, and then xy, x2 y2, sorry, it's x1 y1, and so on, right? So maybe like x sub m inverse, y sub m inverse, xm ym, and then you have this g inverse thing over there, right? Cool. So we wish to be able to write this as a commutator. Yeah, okay, this is actually getting a bit weird, isn't it? That's gonna be the identity over there or something. This is G. So we have to combine things in a way that this can happen. So that's the inverse over there. Okay, cool. It's x inverse, y inverse over there. We can have the whole thing being inverted. That's probably not a good idea. Yep. So you are going to have the, so okay, so we want to write it as commutators. So you would need something like a G and then a ym inverse. Yes. So this part is what we are going to aim for. You'll rewrite this as G inverse ym, and then a G and a ym inverse, but then obviously you need something like ym and a G inverse over there. But then you think about the part in front of it, so xm ym inverse, right? So this part is a commutator, and then you have a ym and a ym inverse over there. So this can still be converted to a commutator completely, and you also have an xm inverse. I kind of forgot that. Yeah. So then xm g inverse is what you want to be having inverted over there. So you just need to introduce this g and then a g inverse like that, right? So then this whole thing is a commutator, right? And then you have g inverse. So this commutator, you basically broke it down into two commutators, and then you essentially shifted this g inverse over here. And so you just wrote this as g x1 inverse x, so y1 inverse x1 y1 and some other stuff, and then you have like xm minus 1 inverse x, so ym minus 1 inverse xm minus 1 ym minus 1, and then g inverse and this stuff, So yeah, let's call this thing as, I don't know, h1 and this as h2, because these are commutators. So these are certainly uh, elements in this subgroup, right? Yeah. And so we just keep doing this. We destroy this commutator by converting into two elements in the subgroup, and then we essentially shift this, and we just keep doing this, and eventually what we'll be left with is just gg inverse, and then a bunch of elements in the subgroup. So it's like h1, h2, so on. Yeah, I should say h2m, whatever, because like there are 2m of these. So okay, and then this just cancels, so just get this thing. Cool. Yeah. So we just proved that GHG inverse is also, you can write it as a commutator. You can generate it using commutators, right? Yeah. So that means it's a normal subgroup. Cool. So yeah, I think this is it. So I'll see you guys in the next video. Bye.